I'm really very grateful that I can speak. I wish I could speak in Ukraine. I visited a few years ago and it was really a great pleasure being there. Very welcoming. I want to tell you a story before I start. The last Devoxx Ukraine, I think I spoke as well. And you sent me this wonderful T-shirt that I'm wearing. It's Engineering a Sustainable World, Devoxx Ukraine. And so you sent it to me, and my wife picked it up from the post office, and we had to pay import duties because it's Ukraine isn't part of the EU yet, and I was a little bit annoyed, but I'm so grateful now that I got the T-shirt because I've got the T-shirt from the last time that I spoke at Ukraine Devoxx Ukraine. So I'm really grateful that you invited me, and I'm really hoping that this fundraiser will make a big difference. As you mentioned, I'm Heinz. I write the Java Specialist newsletter. If you're interested, join that. It's javaspecialist.eu. And if you just want to say hello, say hi, Heinz at javaspecialist.eu. Send me an email. I'll be very happy to engage and just chat. I'm going to give you a little offer later on, as that's my little effort to support what's going on at Devoxx Ukraine. I'm going to give you a three-way split for my Java Specialist Super Pack. It's actually the biggest discount I've ever given on that course pack, but I'll talk about that later, so don't miss it. Stay around if you want to know more. So we're going to talk about Project Loom, what is looming ahead, and how we can be ready for what's coming. And people used to always ask me, when is Loom coming? And I always have to say, I don't know when it's coming. It might be any time, who knows? But you have obviously heard by now that virtual threads are part of Java 19 preview. I actually use that for my website, Java 19 preview. And structured concurrency is also included, but this is included as an incubator module. So that's also there. Let's quickly do something here. So why do we need virtual threads? That's the question. Why do we need virtual threads? Well, the sort of the motivation for this is that asynchronous code can be tricky to debug. Now, that doesn't mean that that you're going to always have an easy time with virtual threads, because as I will show you, there are some situations where virtual threads are also quite difficult to debug. But we have this callback hell and all sorts of issues, but we have been using asynchronous code for quite a long time, and we do have some very well-established patterns that seem to work well for asynchronous code. So, and I'll talk a bit more about this as well. Now, the reason why we went for asynchronous code is that the one-to-one Java thread model doesn't really work too well. All our hardware is limited. All our operating systems were limited as to how many threads, how many platform threads or native threads we can construct at once. And so as a result, we do have some limitations. And this is why they made Project Loom, where you can start millions of virtual threads in a single virtual machine. And what they've done is they've gone through the whole JDK, and they've looked for places where we have blocking calls, and they've tried to patch them so that they're supported by the virtual threads. So anywhere where a thread would block, we now have virtual threads being enabled to not actually block a native thread, but to swap out the virtual thread so that we can support millions of these things rather than just hundreds or tens. So I'm going to show you a little demo where we've got a web page server. We're searching for different search terms. We're going to search the partner websites. Then we're going to also create advertising links. And then once we've got all the results from the partner websites, we're going to collate those results and give a final result back. Now, what we can actually do is we can reorder some of these steps without affecting the final result. For example, we could create the advertising links first and then do the rest, or we can do them at the end, or we can do it at the same time. Of course, we can't collate the results before we've gotten the results from the partner websites. But there are 4 distinct steps. Some of these will involve us waiting, and some of these will involve us using CPU to to generate the links, etc. So here we've got our very basic, simplest solution, which is a sequential processing. And what we do is, first of all, we scan for search terms. That's the first step. That gives us back a list of search terms. We then stream over these terms. And what we're going to do is to do a search on partner site on the search term. And then we're going to convert that to a list. So we end up with a list of search results. And we're going to then create advertising links on the request. The advertising links, in our case, are not going to be dependent on the search, on the results from the partners. You might want to do that, but that would then complicate this whole process a bit. And then lastly, we're going to say results.for each, this : collate result. And that's going to then give us the final result of the web page rendered and pretty for all of us to see. And what I did was I sort of attached some time to each of these different steps. So you've got scan for search terms, some time, and each of the searches, it's all now sequential. They will all happen one after another. And the final time is 4.3 seconds. It's just a number. Hopefully it won't take really that long, but it's just a number to start with. Now, a different way of doing this is to do a search in the background with a callable. And so if we can do a search on all the partner sites in the background, then perhaps by the time that we finished creating the advertising links, some of these search results will already be ready and we can start using them. All right, so let's look at an example for that. Here's our future renderer. What I do now is I scan for search terms. This is still a single-threaded request. I then do a search on partner site inside a callable, and the callable is going to return a list. So what I've done is I've taken the search before and I've simply wrapped it inside a callable. So if you go back a couple of slides, this code, the number 2 over here, that's simply wrapped inside a callable. So we've got the callable which wraps this. And then we've got, and I'll submit this callable to an executor service, and that then gives me back a future where I can get the results in the future sometime. I then do the advertising links in the background, which obviously will consume some resources. And once I'm done with that, I'm going to say results.get.forEach collate results. Now, we're doing something in parallel, but it doesn't actually help us that much. So if you look here, it's gone from 4.3 seconds to 4.1 seconds. And the reason is that the advertising links itself doesn't take that long. It would have probably been better if we'd done the searches in parallel, the searches on the partner sites in parallel. But we're still doing all the searches sequentially, and then we're collating the results sequentially, so we don't really win that much with this approach, with the future, and doing everything inside a callable. So we could also use completable future, which lends itself very nicely for representing a concurrent process. And I've always seen this completable future as a handwritten abstract syntax tree of your concurrency. So what we're going to do is we're going to have each step as a completable future, and then we're going to combine all these steps together with Orloff to do them in parallel. And we are going to have code that's going to complete faster because we're going to be able to at least do the searches in parallel. We're not going to do the collating in parallel. That's going to be single-threaded, but we will get some speed up because at least our searches will be happening in parallel. Now, one thing with computable future is that at the moment, if you just run the computable future with the default settings without specifying a thread pool, then it's going to use either the common fork join pool, or it's going to use a single thread, a new thread per task. A new thread per task. This is the current setting, and it will use a new thread per task if you've got a single core machine without hyperthreading, or if you start up your machine and you say, I don't want to have any threads inside my common fork join pool. In that case, every time that you start it, it's going to make another thread. It's going to make another thread, another native thread, platform thread. So that's kind of annoying. So here's what it would look like. We've got our this is our control flow. we're going to split into two, create advertising links and scan for search terms. And then each of the search terms we're going to search on the partner sites, followed by collating the results, and then finally joining them all together, and then we're done. So the good thing is we can actually now do the searching and the collating in parallel. And this representation, it's your activity diagram, UML activity diagram, looks a little bit like a Petronet from the from the 90s. But the idea is to fork it and then to join the result back together again. And if we code this, it's going to look something like this. We're going to, first of all, have two pools. One pool is for CPU-based tasks. Other one is for IO-based tasks. Two different ones. And the render page will then create a completable future for the request and join that. Joining will wait for the final answer before returning. The render page completable future will execute both the create advertising links and the scan for search terms and then collating the results. So you've got on the one side the advertising links, other one is scanning and then searching and collating the results. So the creating advertising links, this one's quite easy. We're simply asynchronously going to create the advertising links for that request on a CPU pool. So this has nothing to do with IO. We're not going to block on IO. And so we're going to have a relatively small CPU pool. Here you can actually use your common fork join pool. And then when we do this with for the scanning, searching terms CF, so over here we're going to again do CPU pool. We're going to simply scan the request to find search terms, see what are we actually looking for. And after we've done that, we're going to then say search and collate results. This is going to be done using search and collate. So each of them is going to be search and collate. It's going to end up with a final array of completable futures, and that's what we're going to return. Now, what we're going to do is we're going to say search and collate. It's going to first of all search on partner sites and then compose with collate result. So the first is a search, which is asynchronous with the IO pool, and afterwards we're going to collate the result, which is done with the CPU pool. And after all this work, which I don't mind doing the work because we need to do the work, we end up with taking 0.9 seconds. So this is better. It's much better than what it was, but a lot of extra work to get to this nice result. So could we do it simpler? So the first thing is, could we simply create one thread per task? And I would propose that the code would be simpler than if you use a completable future, but it would have some restrictions which would prevent us from using this lovely approach. And this is what it would look like. I would make a new thread, simply new thread with the create advertising links. I'd start that new thread, the advertising links thread. I'd make a collection where I'd first scan for the search terms. I'd get a stream of those. And then for each search term, I would make a new thread, parsing and collate results. And then search, well, actually I'd first search on partner types. That input would be used to collate the results. So it's sort of, the order is not that obvious. It should actually be first search on partner sites, then collate results. But of course, we're calling collate results on the result of the search. And then we start that thread and return the thread. There's actually, in Project Loom, they've got a nicer way of writing new threads, which I'll show you in a moment. But this is just, I'll just try to keep it the same as it was up to now. And we get a list of threads back from this code. We then join the advertising thread. So that waits until that thread is done. And then once we finish with that, we wait until all of these search and collate threads are done as well. So if I've got 10 different partner sites that I'm searching, this is going to start 11 threads, because it's going to have one thread for the advertising thread, and the other 10 would be for the search terms. So that's actually quite a lot of threads each time somebody connects. So if you've got a server and you've got 100 people connecting at one particular time, you're going to have to make 1,100 threads. Most of those threads will sit idle waiting for work. In fact, it's probably going to be worse than that. No, sorry, it's going to be exactly that number, because we're not using any thread pools. So it's a lot of threads for something rather simple. Now, The timing is actually better than with the completable future, but it's the way that I've implemented the completable future. I could have done more optimally, but that would be even more complicated than what we've got at the moment. The problem with this is that it's not scalable. Even if you construct one thread per client connection, that is one too many. And you don't want to get to the stage where you run out of threads, out of native threads, because your system can become rather unstable. It can crash. You can have a complete JVM crash when you run out of threads. In our example, we could be launching dozens of threads per client request. So it simply doesn't scale. And this is why we've got all these other wonderful mechanisms that we use to avoid constructing threads. Now, the virtual threads are a solution that we can use to keep the code relatively simple and at the same time be able to scale. The virtual threads are typically quite lightweight. They normally use less than 1 kilobyte per virtual thread. Although they haven't really optimized that part yet, it's likely that that's going to get better rather than worse. They are quite fast to create. And so, for example, and because they're quite lightweight, you can really have a lot of these things around. They are internally executed by something called a carrier thread. So with normal threading, you're going to have a one-to-one mapping between your Java thread and your platform thread. With virtual threads, you're going to have a many to few mapping, M to N mapping, where M is your number of virtual threads and N is your number of hardware threads. So by default, they're going to have a fork join pool as a scheduler. And they've had to do some work on the fork join pool to be able to do this. But that's what they're using at the moment. And fork join pool is really good at executing short tasks. It's really good at that. So they're using fork join pool, and the fork join pool will be maybe replaced at some point in the future. There was in the beginning an option to specify your own thread pool, your own executor service for running these, for actually running the virtual threads, but they've disabled that for general public because it's complicated enough as it is, or the whole system's complicated enough without introducing another complication of having, us, the common programmers, try and outperform the fork join pool. So it's just a fork join pool. It's not the common fork join pool, it's a different one. And the actual threads are by default daemon threads. The number of threads in this fork join pool for the virtual thread, for the virtual threads, is the number of hardware threads. So if you take runtime.getRuntime.available processes, that will tell you how many carrier threads you're going to have. If the thread is busy, really busy doing something, you'll see that carrier thread busy inside your thread dump. All right, now this can actually, the number of threads can temporarily also increase. So by default, it starts at available processes, but if one of the threads blocks, and it's blocked in such a way that it can't be swapped out as a virtual thread, then it can increase. Now, I'll show you a bit more about the managed block in a moment. But most of the time, if you're blocking either on I/O or with the synchronizers, which are on Java util concurrent, like a semaphore or reentrant lock or a cyclic barrier, any of those, it's going to be moved off the virtual thread's going to be swapped off the carrier thread, and another thread is going to be swapped onto the carrier thread. So you don't have to worry about occupying all of the carrier threads unless you do something stupid, like, for example, infinite loop, or you're doing a wait on a synchronized. I'll talk about that some more in a moment. Now, I promised you at the beginning, I'm going to give you something. And usually I give away a free course, but this time, because we are really trying to do something special for Devoxx Ukraine and for Ukraine, I'm going to do something I've never done before. I'm doing a 3-way split for my Java Specialist Super Pack. Now, this is not a cheap course. It's a bundle of everything I've created, all my courses. There are lots of there. It's like you're going to spend more than 100 hours getting through the material, and you'll get a lot of knowledge. You'll learn a lot about concurrency, and there's tons of useful stuff in there. So what I've done is I've given you a 30%, 33% discount, which I never give such a big discount on this pack. I mean, I usually, when it comes over to Black Friday, I always have a discount, a $500 discount. This is more than $600 discount. And then the remainder, I'm going to give half of that to Devoxx Ukraine, and the other half of that is to offset some of my expenses in running this, because there's a lot of things involved in actually maintaining this material as well. So if you're interested, you can get that here, DevUA, tinyurl.com, DevUA22. This offer you're welcome to share with people, because we want to raise as much money as possible. And it expires next Friday. So Friday the 9th, 22. So please don't miss it. We're going to try and raise as much money for Ukraine as possible. And at the same time, you're getting a discount as well. So, all right, let's get back to this whole rendering. So if the virtual threads are basically unlimited, I mean, yeah, okay, so it is limit. There's always a limit because they use memory, but it's not like platform threads where you can have a few hundred, maybe 1,000 or a few thousand. Here we can have millions of these things at the same time. So why don't we just create a new virtual thread for every task? So just remember what it looked like in the beginning, the single-threaded renderer. We had simply scan for search terms, then we do the list, then we create advertising links, then we collate the result. So what we can now do is we can actually use a new feature where we say thread.start virtual thread, and this is part of the preview of Java 19. So we're starting a virtual thread, and we're passing in a callable or runnable, actually runnable here, where we're saying create advertising links with the request. And then we're going to, again, make a collection, search and collate streams, where each individual request, or each individual term is going to be wrapped again with the virtual thread. And what's nice about the start virtual thread is it accepts a runnable, and it also starts the thread and it returns the thread handle. Normally, the start method will start the thread but not return the thread handle, so you always have to do it in separate steps, whereas now I can do it in a single step. So, so here we make this as a separate virtual thread, and then once I've done all this, it's now running in the background. It's going to make 11 virtual threads, but these are, as I said, virtually free, almost free. Can make lots and lots of these. And we're going to join the advertising thread to make sure it's complete before we finish. And then we can iterate over the other threads we made, the search and collate threads, and join those to make sure that they also are complete before we finish. And so that's again going to take like 0.5 seconds. So it's really, really fast. And this doesn't require us to learn new ways of doing things, except for how we would have done threading before. So it's very similar to what we did before, except that we now have the method start virtual thread, where before we had to say new thread in order to create this. All right, so we can construct virtual threads in different ways. The first way is to say simply thread.start virtual thread with a runnable. This will return a thread that has been started already. Something else they added is builders, both for virtual threads and for platform threads. So you can also say thread.offVirtual, which returns a thread builder for making virtual threads. And I really like how they've done it. They basically used a polymorphic builder, as you can see in the book Effective Java. They've got this idea for polymorphic builder. And so that's a polymorphic builder where if you're doing a platform thread, you're going to have certain methods, like, for example, priorities, a daemon thread, yes or no. Whereas with virtual, you don't have that because you don't have ideas of priorities and daemon on the virtual thread. That's only on the platform thread. So then we construct it, we can start it. We can give it a name, but by default, virtual threads do not have names. They're quite minimalist. So that's one way to make individual threads. Or if you want to, you can even make an executor service. Now, this is not a thread pool because you're going to construct these things and then throw them away once you're done. Because they're so cheap to construct, you're not going to bother pooling them. The reason you make a pool, an object pool, is because what you are pooling is expensive. But if it's super cheap and free to create, then just create it and throw it away. Create it and throw it away, and you'll be fine with that. So Virtual Thread per Task Executor is a really good name. It used to be called New Virtual Thread Executor, but they decided to rename it to make it really explicit that every single time there's a task, you're making a new virtual thread. And then once it's done, it gets garbage collected. What's also nice is that the executor service itself has become auto-closable, which means we can wrap it in a try with resource, and the close will call shutdown and await termination. There's always been a bit of a bother because in the past, you would shut it down, but then you actually wouldn't know that it's been really shut down. You'd have to wait, call await termination to really make sure it's done. But now that gets taken care of for you. So if you were to use executor service, it would look like this. You'd say try. We make the main pool with the virtual thread per task executor. Then we'd submit the create advertising links, and another submit would first of all scans for search terms, and then we'd collate all of the results. So here it's going to do the advertising links and the searching in parallel. And then we're doing the try afterwards. Now, we actually have two nested pools. The reason I've done that is that the moment that you have submitted this job, it's going to call close, and then you can't submit any more jobs. So if you try to submit within the submit back into the pool, you're going to get exceptions. It's no longer, you can't submit anything more into that. All right, so that's how this would look with an executor service. Now, that's actually called, this over here, the executor service, is actually what they call unstructured concurrency. And when I was preparing for this, I was thinking that this was going to be called structured concurrency, but this is actually the unstructured version. And the structured version is going to look a bit different. Now, I mentioned to you that these virtual threads are part of a preview features of Java 19. The preview features are not done, they're not ready, but they do have to be implemented by anybody who calls themselves a JDK, an OpenJDK. So any implementation of the OpenJDK has to implement all the preview features. And that's actually quite challenging because Project Loom has some rather wide-ranging effects. And some of the implementations are struggling to implement them. I believe ARM32 had some issues trying to implement this Project Loom. And unfortunately, the OpenJDK law is you can't call yourself an OpenJDK unless you can also implement all the preview features. And the other problem with preview is that, well, first of all, it doesn't necessarily stay the way it is. It might change from what you've got at the moment until you actually use it. But the other thing is that you can only turn them all on or all off. So you can't say, well, I want to use Loom, but I don't want to use some other thing which is preview. No, when you turn it on, you've got all the preview features. You're also going to have, pattern matching on instance off. I'm not sure if that's a preview, but everything that is preview is then on. So it's either all on or all off. That's on the Java JDK. There's also structured concurrency, which is an incubator status at the moment. And I'll talk a little bit more about the different statuses in the moment. But the incubator is definitely not ready for prime time. But they are working on creating something which will be easier for describing concurrent flows. That's what they're trying to do. And this is, if you want to see more, look at JEP 428. And they're still developing these idioms. I'm not sure if this is the best. I was just hacking this together this morning. I'm pretty sure that this can be done better. But the idea is the following, that we can make a structured scope, a structured task scope that says we're going to shut down if there's a failure. If any one of these tasks fails, we're going to shut down and throw an exception. And that's always a problem, is what do we do with exceptions? If you don't know what to do with those, that's going to be a problem. So here we're going to, first of all, fork on the scope, create advertising links. Then we're going to scan for search terms. I actually think this should also be inside a fork. And I might have to do a nested scope. I'm not quite sure if I need that yet. But as I said, I was still playing around with this just before I came on and didn't have time to to get it perfect. But it is still in flux, and I've seen some really good ideas. Jose Pomard has got some great ideas of how to improve on the standard idioms. So that's all still happening, but the idea is that we have a more structured approach. So I'm not going to go into more details here, except to say that there's more coming on this. All right, I want to look at some other things we need to consider if we're going to prepare ourselves for working towards Loom. First of all, the fork join pool is always configured with your desired parallelism. So it's going to say, how many threads do you want to be able to run at the same time? That's what it's asking. It's not asking what's the maximum number of native threads. It says, how many of these native threads do you want running at the same time? That's what they're looking for. And so if a thread blocks in a way that that the thread, that it can't be swapped out, and then the fork join pool is actually allowed to make more threads if this thread is blocked using something called the managed blocker. And this actually started a long time ago with Java 7. And in those days, only the phaser was a managed blocker. So if you blocked with the phaser, then the fork join pool could create additional threads to increase your parallelism. Then in Java 8, they included the completable future. In Java 9, process and submission publisher. And then in Java 14, they added the abstract queued synchronizer. And this means that if you were to block with a normal platform thread on either reentrant lock or reentrant read-write lock, countdown latch semaphore, any of those, it would actually manage to construct additional threads to keep your parallelism high. They added the link transfer queue, the synchronous queue in Java 17, and in Loom, they added the selector impl. They even added object wait and the old IO. So this all helped to increase the parallelism. If you are blocking a thread with native methods, ideally you shouldn't do that. But if you do that, you can wrap your code inside a managed blocker. And then if you block, at least the fork join pool can create additional threads in order to keep your parallelism high. Another example is where the Java has been changed is with JEP 353 and 373. They've re-implemented the socket and the datagram socket API. And for me, it's always amazing that everything still worked afterwards. But they re-implemented it in order to avoid blocking whilst holding a lock, a synchronized lock. So one of the issues we have is that, first of all, you can use synchronized without a problem with Project Loom. There's no problem synchronizing with virtual threads using synchronized. However, there is a problem at the moment synchronizing and then suspending the thread inside some native code. That's a problem. Okay, so and for example, synchronized wait, inside the wait, they're going to suspend the thread, and that's going to be an issue. What they've done, they've sort of hacked it a bit so that if you do it, but not too often, it will still work, sort of. And what they do is when you call wait on an object, they now see, is this thread a virtual thread? If it is a virtual thread, then they're going to create, or they do it with managed blocker, which will possibly create additional threads in order to keep the parallelism high. But this is an artificial construct that might not work, and you can run out of threads as well. So here I'm making 10,000 virtual threads. Each of them is locking on synchronize and then waiting on the monitor. And once I've done that, I say start another virtual thread, print out done and .join. You'll never see an output. Unless you've got a machine with like thousands of cores, then you might be able to see it. But most of the time, you won't see it. So you should get rid of any place where you're synchronizing and then calling monitor.wait. Replace it with reentrant lock. This is not a problem for thread safety. It's only for waiting and suspending your thread. This is what the code looks like now on object wait. If thread is virtual, use a blocker.manage block in order to wait, and this will construct additional threads if you wait for too long. That's what it looks like. Otherwise, if it's not a virtual thread, just do the normal wait. So we might have to migrate our code to reentrant lock and to stamped lock. Reentrant lock is more complicated than synchronized, and stamped lock is a lot more complicated. I've got a few talks. If you search online, you'll find them where I talk about stamped lock. All right, biased locking is turned off. Biased locking has complicated everything in the JDK, JVM. So they've made it simpler by turning it off since Java 15. And if you've got, for example, an uncontended concurrent hash map, you can actually, on some hardware, notice it being slower. On other hardware, it'll be exactly the same. It just depends on what you're running it on. So I'm going to say that it's very unlikely that if you run your code, that it's going to be slower because of biased locking being off. But what you can try is turning it on and seeing if it makes a difference. Very likely it won't, but if it does, please report it. Thread locals are sort of supported by virtual threads, but they're not recommended. And virtual threads are never reused. We use them and throw them away. So thread locals often don't make sense, except if you want to use them as sort of global variables. But we know that global variables are not ideal, so rather don't use thread local. You can disable them, and I'll show you what happens in a moment. And these have been replaced, again, incubator module, as extent local variables, JEPs 429. So here's the thread local, and I've got with initial that makes the new simple date format, and I'm just printing out when I'm making it. I'm then going to go with the task. I'm going to go 3 times. I'm going to call df.get, and I'm going to do parse. Now, with a standard virtual thread, when I start that with the task, you're going to see on the left-hand side is going to make 1 simple date format, and then it's going to do 3 parses, parse, parse, parse. With the second one, I'm going to say thread.offVirtual, and then I'm going to say allow set thread locals false, and then we're going to start the task and join it. And now you see that every time I do so, every time I call get, it's going to simply call with initial and make a new one and throw it away again afterwards. So you can, obviously that's not going to be what we want, right? So if you need to do some way of sharing state like that, you're rather going to use extent local or use a different mechanism. Something else which has tripped me up a couple of times is that virtual threads do not have a name. They're nameless because they're trying to minimize the amount of state. But they do have a thread ID which takes the place of get ID. Get ID was never guaranteed to give a unique final value, even though it does in most, probably all cases, but you can override get ID to return a different value. Whereas thread ID is final method, and it's guaranteed to give a unique final value per thread. You can never reuse the ID on the thread ID. So you can use this in order to identify your thread rather than a name. Something else is the thread states are a lot more complex. In the past, with a platform thread, we had 6 states. The new state before it's been started, runnable whilst it is running or might run, terminated once it's been stopped or it's exited the run method. And then you had blocked waiting and time waiting states we could be in. A couple of years ago, I actually decided to try to draw the state machine of virtual threads. This was the state in 2020. It's probably changed by now. So don't take this as the final word. I'm quite sure it's changed. But as you can see, it's a lot more complex. You've got new started running versus runnable. They've actually separated the two. Yielding, parking, pinned, parked, terminated, lots of different states. As I said, don't take this too seriously because it might well have changed. But just to show you, it's a lot more complex than it used to be before. But we're still going to see the thread state as before. If it's busy running, we'll see the carrier threads state. Otherwise, you're going to see runnable. So you can see the different states mapping to the virtual threads. Some people think that you can simply take your old code and now apply virtual threads to that. That's not necessarily going to work because, for example, if you simply have a buffered reader and a print stream to communicate, those actually use a lot of memory. I was quite surprised by that. This is the memory overhead of the different streams. So your print stream uses 17 kilobytes per print stream. Your buffered reader is 16 kilobytes, just for a reader. So if you, for example, have let's see, a buffered reader that's reading from an input stream reader, that's another 8.4K, that's reading from your socket input stream, you're going to have like 24 kilobytes just for empty space, because almost all that space is just empty space for buffering. So it's horrendously expensive. It actually used to be slightly worse. This was 25K for the print stream, but they've improved it. All right, something else we have to be careful of are deadlocks. I wrote about this in my newsletter in June. It's surprisingly hard to debug deadlocks in virtual threads. And the reason is that your thread dump will not show you your deadlock. You can see it if you look very carefully. You'll see that, for example, platform thread number 30 is waiting for monitor entry, and it's blocked on an object monitor. So it's waiting for this lock over here, and it's locked on a particular lock. But it doesn't show who has that lock, 43FCE3D90. You don't see who has that lock. You can just see that it's waiting, and you see it's locked on this one. And if you look carefully, you'll see there's a fork join pool 1 worker 1. This is our fork join pool we're using for the carrier threads, and it says carrying virtual thread number 31. It's not moving. It's just staying in the same position. So if you do a couple of thread dumps, you'll see the carrying virtual thread stays in the same position. You won't see at the end, you won't see, hey, found a Java deadlock, but you will see this. And if you then want to find out what's actually happening on virtual thread 31, you have to do some other debugging. You actually have to run that virtual machine with -d JDK track all threads equals true. Obviously, that's going to be more expensive, and you don't want to do that all the time. But unfortunately, if you're deadlock prone, you need to do this. If you have any sort of communication where you have a deadlock between virtual threads and normal threads, or even between virtual threads themselves. But if you've got a deadlock, you can then say J command, the process ID, and then thread.dump to some file with some file name. And if you look inside, you'll see where your virtual thread is busy. So you can see it's in simple lock ordering deadlock mixed threads.java code on 22. At least you can see where it is, but you can't see who owns what thread. That's unfortunately who owns what lock. You can't see that in this view. It gets more fun when you get deadlocks with reentrant locks, because you can see that if it's a virtual, if it's a synchronized, then you can see that the fork join pool worker is blocked and can't be used anymore. And actually, this won't create new threads. This is not a managed blocker. This is going to stop. But with the reentrant lock, the thread gets taken off the carrier thread, and so it's harder to actually find these. Really hard to find. So all I can say is good luck. The other thing is, if you've got a system that works fine with asynchronous code, don't try and change it to Project Loom. It's not necessary. Virtual threads will help to alleviate some of the pain if you're starting from the beginning, but they're not necessarily going to be faster, and it's probably going to be quite a lot of work and won't achieve much to try and retrofit it. I saw Vertex try to do it. I saw that, was it Jetty? I think Jetty tried to do it as well, to retrofit it. And they didn't really find very many places where it really would be better to do it, to retrofit it. And so they recommend you don't try and retrofit asynchronous code. There's actually apparently a project happening where they're trying to do a server simply with Loom, and I'm not sure when that will be ready either. So if you want to have back pressure with virtual threads, you're going to use something like semaphores or blocking queues, but you have to be a bit careful because semaphores are a rather primitive mechanism, and you've got no record of who owns the semaphores. When you give a permit to somebody, you lose that information as to who has the permit. And if you lose a permit, there's no way of getting it back. So you reduce your parallelism, and therefore you then have too much back pressure, and you can't use the system properly. So even though that is the recommended way of sorting out the back pressure with Project Loom, it's not necessarily going to be that easy. So always the question, when it will be ready? I mentioned at the beginning, it's currently available in Java 19 preview. I'm using some parts of Project Loom on my server, javaspecials.eu. Makes some things better. And some parts are already in mainstream Java, like the networking and so on, I've put in there already. But Java has different levels of readiness. Either something is part of the OpenJDK, or it's a preview feature which is mostly ready, but they might still change things. And when you compile it, it's only for that particular preview version. So you can't take preview 19 and run it on JDK 20. You always have to recompile it for the latest Java version. But the problem, as I mentioned, is that if something is preview, it has to be supported by all Java runtimes of that version. Then you've got experimental features, which don't have to be implemented by all runtimes, an incubator, which is still, well, we're still trying to figure this out. All right, don't forget the 3-way split. It's going to expire on Friday the 9th. So let's have some questions. I've got a couple of 2 minutes for questions, I think, left over. Is that right, Katerina?
Yeah, thank you, Heinz. Yeah, we have actually 3 minutes, but I don't see any questions yet to you
No
in the chat.
questions.
So
No. Either it
usually,
was completely useless talk because everybody knew everything already, or there's or something else. Let's hope it's not the truth.
usually I assume if there is no question that everything was clear. Let's hope so.
No, or nothing was clear. It's one of the two. It's either completely clear or completely confusing.
Yeah. Okay, so a couple more seconds, dear friends, for you to put some questions while Heinz is with us, or otherwise, if it was not quite clear, you're going to have a recording. You can watch it once again, probably then get in touch with Heinz and ask, but yeah, it would be easier
Yeah,
to
you're
do
welcome to send
this
me an
right
email.
now.
Heinz@javaspecials.eu. Absolutely.
Great, thank you. So, still no question. Then let me thank you, Heinz. Thank you once again for joining. We really appreciate this. We're honored to have
Thanks,
you,
Katrin.
and really hope to see you soon in Kiev on a Devoxx Ukraine. Hope
Yeah,
so.
that'll be great.
And
Looking forward to it.
yeah, yeah.